We are ready to continue with our unit on heat. Last time we were talking about methods of heat transfer, conduction, convection, and radiation, and our problems really are only for conduction and radiation. Hopefully you've maybe had a chance to look at that. Maybe not. Maybe you were just in the sort of post contest euphoria for a few days. But either way, I would take a look at those soon. Today we will consider what happens when heat flows into something. So before we talk about how it flows, today we'll talk about what happens. So typically, we call Q the amount of heat flow. So this is, measured in joules. And if we allow heat to flow into matter, one of two things can happen. The first thing is the temperature can change. So if we want to see how heat relates to temperature change, then typically the amount of heat flow is proportional to the change in temperature. A better way to think of it is that the change in temperature is proportional to the heat flow. The change in temperature is also inversely proportional to the mass. So what does that mean? It means the more mass you have, the less temperature change you're going to get. So we could say that the temperature change is equal to some constant times Q over the mass. And if we rearrange this, then Q would be equal to the mass times, well, technically it's some other constant, but it's still a constant. So this constant we're going to call C times delta T. So the constant here of proportionality is known as the specific heat capacity, often just called the specific heat. So what's the specific heat exactly? Let's rearrange and solve for it. It will be Q over M times delta T. So it's the number of joules that is required to raise the temperature of 1 kilogram of stuff by 1 degree Celsius. So if you take water, for example, it takes around 4,186 joules to raise the temperature of 1 kilogram of water by 1 degree Celsius. So if we wanted to know the specific heat of water, it's 4,186 joules per kilogram degrees Celsius. That's what that means. It takes 4,186 joules to raise the temperature of 1 kilogram of water by 1 degree Celsius. If we look at something like aluminum, I think it's about 900 joules per kilogram degrees Celsius. In general, this is not a number you're supposed to have memorized. It's something we look up in a table, just like we would look up, densities of things in a table. But the specific heat can vary a lot. Something with a high specific heat then is very expensive in a sense to raise its temperature, but it also wants to hold on to its temperature a lot. If you look at water, that specific heat is one of the highest we will ever see. And that means it's very, very hard to change the temperature of water. That's why the swimming pool, if you want to go swimming, it's going to be like 85 degrees this weekend, but I dare you to go jump in a swimming pool because the swimming pool is going to be still really cold. okay, unless you spend, someone spends a lot of energy and money to heat it. So ordinarily, even by Memorial Day weekend, pool's open, but the swimming pool will be very, very cold at that time, because it's almost like it has a lot of mass. It doesn't want to change. We might call it a high thermal mass. So whereas a piece of metal can go up or down in temperature very easily. For copper, I think it's 387. So that's less than, 1/10 of the specific heat of water. So let's just do an example to see how much heat it takes to raise the temperature of some water. Maybe you want to boil some water. So we're going to find how much heat is required to raise the temperature of 2 kilograms of water. That's about 2 liters, roughly a half a gallon, from 20 degrees C to 100 degrees C. So that's just to get it to the boiling point. It doesn't just instantly boil, as those of you who cook stuff know. Once you get the water, it instantly turns into steam. You have to keep supplying heat and keep supplying heat and keep supplying heat in order to turn all of that water into steam. So I'm not talking about the boiling process. I'm talking about just first getting it up to the boiling point. So we would say Q equals MC delta T. The mass is 2 kilograms. Specific heat is 4,186 joules per kilogram degrees Celsius. Delta T, because it's a delta T, we can use Celsius. We don't have to convert to Kelvin. We're going up 80 degrees, so that's a plus 80 degrees. If we were decreasing the temperature, we would get a minus sign for delta T, and that would mean we have to remove heat to do the same process, or I guess to do the reverse process. So this is 6.697, let's just say 6.7 times 10 to the 5th joules. So that's a lot of joules. That's, 2/3 of a million joules, roughly. So that either means joules are very small, or it takes a lot of heat to raise the temperature of water. Joules are not that small. What's a joule? A joule is the energy to raise 1 Newton a distance 1 meter. So Newton's about 1/5 of a pound. So the energy, if you pick up sort of 1/5 of a pound from the ground up to 1 meter, that's 1 joule. So, 2/3 of a million joules is like lifting 2/3 of a million newtons, by 1 meter. That's a lot of energy. So why is it so expensive? Because when we want to raise the temperature, that means we're raising the kinetic energy on average of all of the particles in that, in the 2 kilograms of water, and there's a lot of particles there. So to raise the temperature even by 1 degree can be pretty expensive. Okay, any questions so far? Have any of you seen this before in another class? Christina's seen it, Lauren's seen it, Sumner not seen it, Carl. Okay, so often you see this in a chemistry class, but not all chemistry classes. Same thing, we don't always see it in physics class, but I'm not going to spend a huge amount of time on it because I think it's fairly straightforward, and we don't really need it for our goals, but we do want to be aware of it. So the basic idea is this: if I want to, change the temperature of something, it's going to require adding heat, and the more mass we have, the more heat we need to add to raise the temperature. Okay, so that's the key idea. What about, what was the other thing? I said that there were two things that can happen when we add heat. So the second one is that we can change the phase. So what does that mean exactly? That means we change the phase of matter from solid to liquid or liquid to gas, or maybe we go backward, we remove heat and we take a gas and make it condense into a liquid, or we remove more heat and we make the liquid freeze into a solid. So in this case, the amount of heat to change the phase is really only, there's no temperature change when we're changing the phase. When we add heat, we want to melt some ice or something. When we add heat, the heat goes all into the phase change and doesn't really change the temperature until the phase change is complete. So the amount of heat is really just proportional to the mass. That's it. And we could say then it's equal to a constant times the mass, and that constant is L. L stands for latent heat, but we can have two main varieties of L, LF or LV. So L is the latent heat of either fusion or vaporization. That's what the F and the V stand for, fusion and vaporization. So let me kind of map it out for you. We have three phases: solid, liquid, and gas. And if we go either solid to liquid or liquid back to solid, this is known as fusion. And if we go liquid to gas or gas to liquid, this is known as vaporization. Now, which way we go has to do with the sign of this Q. So we should put a plus sign or a minus, plus or minus in there, because we either have to add heat or we have to remove heat. Generally, we're adding heat if we go up the ladder to a hotter phase, and we're removing heat if we go down the ladder to a cooler phase. So that should make sense, right? We don't add heat to water to get it to freeze. We have to remove heat from water to get it to freeze. And likewise, we remove heat from steam to get it to turn into liquid. That's why the shower, the mirror in the shower gets all covered in little water droplets, because there's steam in the air. As the water evaporates, the hot water coming out of the shower evaporates, you get some steam in the air and it hits the cold mirror, and the mirror, being colder, is going to remove some heat from the hot steam, and then that steam is going to undergo a phase transition and become liquid water. Okay, any questions about those three phases of matter and the transitions there? Okay, so when we look up the latent heat, it's just like the specific heat. We look on a table, but the table's generally more complicated. It's going to have a lot of information. It may have, for water, for example, we will find the latent heat of fusion on that table, but also the latent heat of vaporization. Likewise, we need to know what temperature these things occur. So for water, the melting point or freezing point is 0 degrees Celsius. So that information will be on the table. For the boiling point, we know it's 100 degrees Celsius, but that's also on the table. We know it for water, but we don't probably know the melting point of copper off of the top of our head, or the freezing point of mercury, or anything like that. So you can find all that in the same table that's in one of our 2 problem books when we're solving problems. Let's do an example with water, though. and find how much more energy that water that we just brought up to boil, how much more energy is required, or more heat is required to make it completely boil. What I mean by completely boil it is we turn it into 100% steam. There's no water left in the pot. Now, this is something that, you know, I've done a few times. I'm kind of embarrassed to admit it. I put some water on. I'm going to make some pasta or something, and then it takes so long for it to get to boil. So I just go and I do something else, and then I forget that I'm boiling the water. And then, like, you know, sometime later, I smell a terrible smell coming from the kitchen, and I go and look, and okay, my pot is ruined. It's just dry. And has anyone ever done that before? Sumner, you've done it? Yeah. Lauren, have you done it? Yeah. You guys have a sense how long it took before the water was all gone? Was it quick? Was it long?
That was fairly long.
I mean, it was probably over an hour before it was all gone. So, you know, it probably takes 15 minutes to bring it up to a boil. It feels like it's half an hour, but it's probably only 15 minutes. But then I've a lot more times I have done this and then realized, oh, crud, you know, and run into the kitchen and the water's low, but it's not gone. It's low, and I'm like, oh, now I got to add more water and then wait for it to boil again. But let's get a sense how much more energy and therefore how much more time it takes for this to happen. So that this would be the latent heat. So we go back and look at this. We want to go from liquid to gas. So that's vaporization. So the latent heat of vaporization, if we go to our table, it's 2.256. Some tables just say 2.26 times 10 to the 6 joules per kilogram. So the amount of heat is just m times the latent heat of vaporization. We also have to know whether we want a plus sign or a minus sign. So because I'm going liquid to gas, I want a plus sign. I have to add heat to get the water to turn to steam. That's the way I think of it. I add heat, so I use a plus sign. So that's going to be 2 kilograms times 2.256 times 10 to the 6 joules per kilogram. Make sure you're using kilograms here, or else these don't cancel. And we're going to get 5.512, I think, times 10 to the 6 joules. So that is, sorry, it's 4.512. It's a little bit hard to read here. 2.256. So that's like 4.5 million joules. It took 2/3 of a million joules to bring the water up to a boil, and then another 4.5 million joules. So if we maybe divide those two numbers, it's about 6.7 times as much heat to change the phase versus just raising the temp. Now that's a little bit specific to water, because water has, you know, very high latent heat of vaporization, and also the temperature difference between, you know, freezing and boiling is very small, only 100 degrees between the two. So for some metals, like, you know, some other things like maybe gold, you have to spend a lot of heat to raise the temperature because the melting point is much higher. And so then it's not always going to be such a big imbalance. But in terms of time, if it takes you 15 minutes to get the water to bring it to boil, it's going to take, more than 6 times, so that much before it's all gone. That's like an hour and a half. And that's probably why some of you have never done it. Probably you've forgotten for 5 or 10 minutes, but then you go back and, there's still plenty of water there. Okay, any questions about the latent heat or changing phase? All right. So now I said that while the phase change is happening, the temperature doesn't change. And that's approximately true, although, if you have a big body of water, you can get different regions with different temperatures within that body of water. So for example, when you're heating up the water, I mean, normally though, because of convection, if you're heating water, the heat is going in at the bottom, and that hot water rises and it flushes cold water down and it circulates things. When we melt ice, I had this experience when I was in like 7th grade, and it still sticks with me. That was sort of an illustration of this idea that while the phase change is happening, the temperature can't go up. When I was like in 7th grade, I lived in Seattle, and there was this particular mall that I used to I take the bus to this mall. I loved going to this place. And one day I was thirsty, so I went to a little, it was like a kind of like a Chinese food carry-out place, like just takeout. And I asked the woman if I could have a cup of water, and she said, sure. And she took a big styrofoam cup and she scooped up shaved ice. She filled it with shaved ice. And then she had boiling water from the teapot. And she just took the boiling water and she dumped it into this cup of ice and she handed it to me. And I kind of like looked at her like, what are you trying to do, lady? You're giving me, you're giving me boiling water in ice. And she said, well, go ahead, take it. It's good. You try it. It's good. So very skeptically, I took a drink of this water. And it was the coldest, best cup of water I've ever had in my entire life. I'm still thinking about this cup of water, decades later. It shocked me. I couldn't believe that she poured boiling water into ice and that instantly that boiling water was cooled down to 0. And that's really what happened. All of the heat in that boiling water went into the ice. And because the ice is shaved, it has a lot of surface area for its volume. And that means the heat can transfer very quickly. So it basically melted, I'd say 90% of that ice. And it left just a few little chunks, like a little crust of ice floating on the top. And everything had dropped down to 0 degrees, Celsius, like instantly. It was way, way better than taking kind of lukewarm water from the tap and pouring it in ice, because that lukewarm water, it doesn't melt the ice very quickly. And if you have big ice cubes, it takes a while for them to melt. So I've mentioned this to students in the past, especially nurses who always have access to shaved ice, or at least ice pellets, and told them, they should go to work and try this out. Get the shaved ice, and go to the teapot and pour that piping hot water for tea right in the shaved ice and drink it. And it's going to be the best water you ever had. And they've all come back to me and said, yeah, it was actually amazing. So if you have access to that somewhere in your life, try it out. Shaved ice, boiling water. It's going to be like a religious experience with your water. Unless you're one of those people who doesn't drink water, then I don't know what to do. All right. So let's kind of try to put these things together. The sort of climax of this story is that by using these two formulas, we can figure out essentially what's going to happen anytime we mix different samples at different temperatures. So let's just suppose we mix let's say 500 grams of ice at 0 degrees Celsius. So it's just barely at the freezing point. We can have ice at minus 10 degrees Celsius. That's a different story. We would have to first heat up the ice from minus 10 up to 0. I'm not talking about that. I just want to assume it's already been pre-warmed up to the melting point. And let's say 800 grams of hot water at 90 degrees Celsius. And we want to find the final temperature of the mixture. We're going to assume we do this in like a styrofoam cup. So the styrofoam cup really doesn't absorb barely any of the heat. So I'm just going to ignore the cup. But if this is in, say, an aluminum, pot or something like that, we would have to include the pot too, because it's going to also change its temperature during this process. So right now I'm keeping it as simple as possible. So the principle here is that if the system is isolated, we can say the sum of the Q's equals 0. So all of the heat transfers have to add up to 0. So what this means is, the hot water is going to leave the heat is going to leave my hot water. That's one Q. And then there's going to be another Q that melts the ice. And if we melt all of the ice, then there'll be another Q to warm up that sort of freshly melted ice water up to some final temperature. So the problem with these kind of problems is we don't exactly know what's going to happen, so we have to make a guess. So for example, there's a little bit of an uncertainty here. Are we going to melt all of the ice or just some of the ice? So if we only melt some of the ice, then the final temperature is just going to be 0. Because in that scenario, what happens is we pour the boiling water in, some of the ice melts while my hot water goes from 90 down to 0. But once my hot water's down to 0, if I still have some ice left, there's no heat left to melt that ice. So we have two possibilities. We could melt some of the ice, and then the T final is going to be 0 degrees Celsius. Or we melt all ice, and the T final is going to be greater than 0 degrees Celsius. It would be very, very, very accidentally lucky if we melt all of the ice and just at that moment we lost all of the heat from the hot water. Normally, if we melt all of the ice, our hot water will have cooled only down to maybe 20 degrees or 10 degrees, and there's still then going to be this mixing that goes on until the whole system is at the same final temperature. That's the way it goes. Heat is going to flow until the whole system is at the same final temperature. So with these two possibilities, if we're going to just melt some of the ice, we would have, one process, one of the Q's is just to melt some ice. The other process, so that's all that happens to the ice. Some of it melts and then it stops there. The other process would be to cool the hot water. And those are the only two processes that happen. We melt some ice, and during that time, the hot water cools down somewhat. How much it has to actually cool all the way down to 0 there. Now, it's possible we have so much ice that the hot water cools down to 0, and if our ice is really cold, we could even freeze some of that hot water. So there's lots of possibilities, but these are the probably two most likely ones. If we melt all of the ice, then what's going to happen is we have a Q to melt all ice plus a Q to warm the melted ice, and then plus finally a Q to cool the hot water. Now, it doesn't matter the order we list these terms, but I always like to just conceptually start with the cold stuff and say, what's going to happen to the cold stuff? And then after I get everything that happens to the cold stuff, in this case, it's two things. In the first case, it was just one thing. Then I add in what's going to happen to the hot stuff. Now, we might have more than two substances. Again, if we have an aluminum pot, then we're going to have another term that's to warm up the pot or to cool the pot, depending on, you know, which way it wants to go. Depends who's winning, the ice or the hot water. So let's just make a guess. If we had to make a guess, how, you know, what do you think is going to happen? We've got some ice and we're adding hot water. The volume of the hot water is almost double the volume of the ice. Do you think it's going to melt all of the ice or just some of the ice? Anyone have a, we just have to make a guess, and that's the problem here. We have to make a guess and then solve it and see what happens. So let's vote. We'll just vote what you guys want to try. Who wants to try the first option, that we just melt some of the ice? Raise your computer hand if that's the one you want to try, because you think that's what's most likely. Okay, raise your computer hand if you, okay, one person. Raise your computer hand if you think the other option is more likely. We're going to melt all of the ice, and then the temperature is going to go up. So we've got 3 people there. Okay, so we'll try that one. Okay, we'll try this option. We'll just go to the next page so we have plenty of room. All right, now we just write down our terms. To melt the ice, we're going to have M of the ice times the latent heat. We need to know which latent heat it is. Is it latent heat of fusion or vaporization? What do you guys think? To melt the ice, which one is it? Is it latent heat of fusion or latent heat of vaporization? Christina?
Be fusion, I think.
I don't know if you were talking. I see your like name is lighting up, but I don't see you and I'm not hearing you. Anyone else?
It would be fusion, I think.
My sound is turned off. That's it. My sound is turned off. I think it was turned off. So, well, what is it? Latent heat of fusion or vaporization?
Fusion.
Fusion. I'm sorry, Christina. I'm sure that's what you were saying, and I just couldn't hear you. And then, do we want a plus sign or a minus sign? Do we have to add heat to melt the ice or subtract it? Still can't hear you.
Positive.
Can you guys hear Christina? Okay, I heard something. I didn't. Yeah, I hear it now.
Okay, cool. I think we need to add heat.
Okay, that's right. We want to add heat. Now we want to warm the melted ice water. So the change of temperature is always, it's always a plus sign in the formula because the delta T can be either positive or negative. So this, we have to be careful. This is mass of the ice, but it's the specific heat. If we look on the table, we'll find specific heat of ice, but it's not ice anymore, right? It's been melted. So we need to be careful and use the specific heat of water. And then finally, we've got to cool the hot water. So that's going to be M for the hot water times C of water again, times delta T. And we should label the two delta T's differently. We can label delta T for the ice water and delta T for the hot water. Okay, it doesn't really matter how you label it, but they're going to be different changes in temperature. The cold water is probably not going to warm up too much. The hot water is going to cool down a lot. Now, what we're looking for here, this is all equal to 0, is the final temperature. And the final temperature is inside of delta T. So we have to open up the delta T. That's going to be mass of the ice, specific heat of water times T final minus T initial for the ice water. So T I W. And for the hot water, we have M HW CW delta T, not delta T. Going to open that up also and have T final. They're both the same T final, but they have different T initials. So we have minus T initial HW for the hot water. And the T initial for the ice water, that's just 0, so we can just cross it out. But for the hot water, it's going to be 90. We cannot cross that out. Now, we want to keep everything that has T final on one side. So let me underline the terms that are going to have T final. Those are going to stay on the left-hand side. We have MI CW T final plus M hot water, C water, T final. And everything else has to move to the other side. So we're going to have minus MI times latent heat of fusion. And then the last term, let me underline what's moving across. The last term would be what you get when you have mass of hot water times seawater times T initial hot water. It has a minus sign in front, so when we move it to the other side, it gets a plus sign. So that's mass of the hot water, seawater, T initial for the hot water. And now we just do a little bit of algebra to solve for T final. So T final factors out. We have MI CW plus M hot water CW equals minus MI latent heat of fusion plus M hot water C water T initial for the hot water. And then we want to divide both sides by the quantity in the parentheses. And there's our expression for the final temperature. Now, before we solve for it, I want to talk about what if we made the wrong guess? Okay, what if we made the wrong guess? Well, then the answer we get is not going to make sense. So we need to think what kind of answer is going to make sense before we get it. What are we expecting T final to look like? If you had to say, you know, a range of temperatures that would make sense, and some other range that wouldn't make sense. Let's look at our question again. We're taking some ice at 0 degrees C, we're mixing with hot water at 90 degrees C, and we're looking for the final temperature. What's the type of number we're looking for? Anyone have just a sense like what kind of expectation? Are there temperatures that are out of bounds that wouldn't make any sense? What temperature, if we get a certain final temperature, what temperature would not make sense? Let me write
0 degrees.
Okay, 0 degrees doesn't make sense if we melt all of the ice. I mean, it's technically possible, but very unlikely. What makes even less sense than 0 degrees?
Negative degrees, like a negative temperature.
Right. Would it make any sense to take ice and hot water and you put the hot water into the ice and the final temperature is colder than the ice started? It wouldn't make any sense, right? What else would it make sense?
If it turns out to be hotter than the water turns out to be hotter than the temperature of the water when it starts.
Exactly. That would also not make sense. So you understand what I'm saying. If we get an answer that's less than 0 or greater than 90, then we made the wrong call. But if I get a number between 0 and 90, I mean, I don't know if it's going to be 10 or 20 or even 60. Those are all possible, but they're not like impossible, right? They just, maybe I expect it to be a low number and maybe my expectation's not right. But that's the kind of thing I'm talking about. If we get an answer that's impossible, then we pick the wrong choice. Now let's go ahead. I'm going to write up here the latent heat of fusion of ice. This is something we look up in a table. 3.34 times 10 to the 5th joules per kilogram. So let's put all these in. We have a minus, let's see, my mass of the ice was 500 grams. So let's convert that to kilograms. 0.5 times 3.34 times 10 to the 5th, plus the mass of my hot water. I'm going to convert that to kilograms too. Although technically, because I'm going to have mass on the top and bottom, if I kept everything in grams, they would still cancel out. So it would be okay in this case if I kept grams. So specific heat of water is 4,186, and the initial temperature of that hot water is 90 degrees Celsius. And then we divide by the mass of my ice, 0.5 times 4,186, plus mass of the water, 0.8 times 4,186. And now we're just going to get a number and see what we get. I get 24.7. Anybody get the same thing? Anyone get something different? 24.7 definitely makes sense to me. So I think that's probably right. Let me know if you wind up with a different number at the end. Okay, so this would indicate we made the right guess. What if we made the wrong guess? I mean, that is, what if we had picked option 1, that we only melt some ice and we cool the hot water? Well, then we would basically be assuming the answer. We would be assuming that the final temperature is 0 degrees Celsius. So how do we know if that's correct? Well, what we could do is we could solve for the mass of the ice that we melt and see if that makes sense. So under the assumption we melt some ice, we would solve for the mass of the ice. And as long as we get something under 500 grams, then we're in good shape. That means we made the right choice. If we get something over 500 grams, it doesn't work. So let's just see how that would work. So what we would do is we would say we're going to have mass of the ice times latent heat of fusion plus mass of my, I only have one water now. Well, let's just call it hot water again anyway. Specific heat of water, delta T for the hot water. And the mass of the ice, latent heat of fusion, would be equal to minus mass of the hot water, specific heat of the water, delta T for the hot water. And my mass of the ice would be then, just dividing both sides by latent heat of fusion, be minus M hot water, seawater, delta T hot water over latent heat of fusion. So when we put these numbers in, we have minus 0.8 times 4,186. The delta T for the hot water would be minus 90 in this case, because we're assuming the hot water goes all the way down to the freezing point. And then we divide that by 3.34 times 10 to the 5th. and I get 0.90 kilograms. So in other words, I would have to melt 900 grams of ice to bring that hot water down to 0. And I just didn't have enough ice to do it. So if I had picked the first choice, when I got this number, I would have said, oh, rats, you know, that means I made the wrong choice and I would have to try the other thing. Now, when you practice this, you can kind of start getting an intuition what's going to happen. And you can also play around with the numbers a little bit. You know, for example, you could just kind of test how much heat does it take to cool the hot water down to 0, and you could test like how much heat does it take to melt all of the ice and see which one is bigger. And that would give you an intuition what to do. But I personally would just say, pick a choice and try it. You might get lucky. It might be right. And if it's not right, you know what to do after that. Lauren, do you have a question?
Yeah, so what were you saying that mass has to be then to say if it was right or wrong?
Okay.
Like, was it need to be near?
Yeah, let me ask you that. What the option we have is that we're going to melt some ice. So if we have 500 grams of ice, what kind of answer would it make sense?
Oh, like something very small then.
Well, I mean, very small would not be impossible. What amount of ice would be impossible?
Like a larger number, or like a larger number than that?
Larger
Or
than,
smaller than the 500?
yeah, exactly. Larger than 500. If I come out and I see that I have to, what I did here, I have to melt 900 grams of ice. Well, I don't have 900 grams. So that can't be how much ice melts. A negative number for the mass would also not make sense. So the number should be somewhere between 0 and 500, because my assumption is that we melt some but not all of the ice. So I should get an answer somewhere between 0 and 500 grams.
Oh, is that in... Oh, I thought that was in grams. I thought that was 0.90 grams. That's 0.90 kilograms. Oh, okay.
That's right. This is kilograms, so which would be 900 grams. So that's why it doesn't make sense, because it's big. It's too big. Okay, so as I said, I'm not going to focus too much time on these kinds of problems. You do have a little bit of homework, so you should practice it. But we're going to be using this this concept in a different context, so we'll kind of hit it again. So we're going to be moving into now the full idea of thermodynamics, and here's the basic idea. We now know that temperature is nothing other than the measurement of the average kinetic energy of the particles in our system, and we know that heat energy is just kinetic energy. So can we find a way to turn the kinetic energy of those individual particles into kinetic energy of something large, such as an automobile or a train or something? Can we take that heat energy and convert it into mechanical energy to do some work for us? The answer is yes, we can. Now that we are aware, now that we understand that it's really just the same stuff, we can do that. So that's what thermodynamics is really about, the changing of heat energy into work energy, or using work to make heat flow in an unusual or unpredicted way. So we're going to discuss today the first law of thermodynamics. And before you get intimidated by that name or excited, depending what type of person you are, it's not really intimidating, and it's also not that impressive. So basically, let me say it in words first, and then I'll write a formula. We now know that, we used to think that if we did work, we would get a change in the energy, okay, of a system. And now we've just learned that there's another way to change the energy of the system, namely adding or removing heat. So technically, the first law of thermodynamics, all it's saying is that there are two ways to change the energy of the system now, instead of one. So we could say delta energy is equal to heat plus the work, kind of the net work on the gas. Okay, so in other words, it's just conservation of energy. It says the energy doesn't change unless we change it. We now have two ways to change the energy instead of one. We can do work on the gas to increase or decrease its energy, depending if we do positive work or negative work, or we can add heat or subtract heat. Those are the two ways. Now, the notation is not, this isn't really the notation that is typically used when we study thermodynamics. So instead of calling it delta E, most books call it delta U. Okay, so this stands for the internal energy. So delta of the internal energy of the gas. So it's internal energy means precisely that energy that's the total kinetic energy of all the particles. That's the internal energy. And the only ways we can change it, we can do Q, and normally we don't write the sigma, the sum of, we just say the work done on the gas. Or an alternative way to write it is to say that delta U equals Q minus the work done by the gas. So these are actually totally equivalent, just two different ways of thinking about it. And let me try to explain what the difference is between a work done on a gas and work done by the gas. So the way we conceive of work here is we imagine we have kind of a cylinder, and inside that cylinder is another cylinder that's known as the piston. Now we have some gas inside this chamber. And we can do work on the gas by pushing the piston down. If we push the piston down, we compress the gas, and that would be called doing work on the gas. Or we could do something else. We could allow the gas to expand. Maybe the gas is under pressure. So we allow it to expand, and as it expands, it pushes this piston up. We would then call that the work done by the gas. So the difference is, are we pushing on the piston, or is the piston pushing on us? This is really just Newton's third law. We have a force times a distance, and the difference between work done on the gas or by the gas is whether we're talking about the work done on the force on the gas or the force by the gas, the force the gas exerts on us. That's the action-reaction pair. Now, most books take this point of view because our goal is to build an engine that will do work. So we're focused on the work done by the gas. The gas is going to do some work. So let me say the first law of thermodynamics in the second formulation. That's the one we're going to use. What is it actually saying? It says we can change the total energy in the gas by adding heat. If we put in heat, the temperature is going to go up. That is, the energy inside the gas is going to go up. But if the gas does work, well, when it does work, it's transferring energy outside of the system. So it's sort of giving us energy, and that would represent a subtraction. The work done by the gas means the gas is losing energy, kind of like when you make a payment, you're losing money. Okay, so the work done by the gas is like the gas is making a payment, whereas work done on the gas is like we're making a payment to the gas. We're adding energy to its account. So that's the difference. Now let's try to focus on what happens if the gas does work. So if the gas does work, there's going to be, you know, an upward, my pen tool, an upward force. And then what will happen is this piston try that again. It's going to move up. So if we wanted to compute work using our regular old work formula, we would say the work done by the gas is equal to the force times delta x, where delta x is the distance that the piston moved. Well, the force would be equal to pressure times area, where the area is the area of the face of the piston. And the area times delta x, we could think of that as sort of the change in volume. That the gas experiences. So the work done by the gas is pressure times delta volume. So what we're doing here is just converting our units. Instead of force and displacement, we're converting them to more of a gas or fluid unit, pressure and change in volume. If I want to know how much work the gas does, I have to know what's the pressure and then what's the change in volume, and that will give me the total work done by the gas. The work done on the gas would just be minus that number because it uses the opposite force. So from time to time, when we're solving a problem, it may ask us to find the work done on the gas, or it may ask us to find the work done by the gas. So we have to kind of be aware of these two different ways of thinking about the work. Most of the time in the formula, so they don't specify, they don't say W by gas or W on gas, they just say W in the equations. So whenever we see W, it means by the gas. That's how these problem books that's the decision that they've made. Okay, let's just do a sample problem to see how that's going to work. Okay, suppose we have 2 liters of gas at 3 atmospheres of pressure. Okay, the 3 atmospheres of pressure expands to 5 liters. How much work is done by the gas. How much work is done by the gas? So we have the work done by the gas is equal to P times delta V. And I should put in some fine print at constant pressure. Because if the pressure is not constant, then as the gas expands, the pressure might go down, and we wouldn't know what pressure to be using in this formula. So this, for now, we're just doing this at constant pressure. That's going to be 3 atmospheres times the change in volume is 3 liters, which would be 9 liters times atmospheres. But that's not the kind of unit we want. We don't want liters times atmospheres when we talk about work. We want joules. So what we need to do is we need to change our units. So, and put the pressures into Pascal. So 3 times 1.013 times 10 to the 5th pascals. Remember, a pascal is a Newton per square meter, so I'm going to write it that way so we can see how the units are going to work out. And then 3 liters, we can convert that because 1,000 liters is 1 cubic meter. And so we're going to get, at the end of the day, meters squared on the bottom cancel 2 of the meters on the top. We get Newton meters. So if we stick with pascals and cubic meters, then we get Newton meters, which are also known as joules. Okay, so I get 911.7 joules. Okay, so how do we get the gas to do this? How do we get the gas to do this? Well, what happens is we've got this gas in the piston, and we add some heat. And when we add heat, those particles are bouncing around faster, and they start pushing harder on the piston. But if the piston is under a constant load, that means there's a constant pressure, then it's going to push the piston as the particles inside start moving faster and faster. They're trying to create a higher pressure, but the piston just slides to allow that pressure to remain equal. If we graph this process, making a graph of the pressure versus the volume, we start at a point that has 2 liters for the volume and 3 atmospheres for the pressure. And then the volume increases up to 5 liters while the pressure remains constant. So this process in this graph would look like a horizontal line. Where would the work be in the graph? Well, the work would be the pressure times the change in the volume. My change in volume is right there. The pressure is there. And so technically, the amount of work done is just the area underneath the line. This gives us a little bit of a hint at how we can handle the work when the pressure is not constant. In general, we could say the work done by the gas is just equal to the area under the curve. And there's a plus or minus sign there because we don't know when we draw the process. Before I draw the process, I don't know if I'm talking about the gas expanding or contracting. If the gas expands, then that is work done by the gas. The gas is doing work. But if the gas contracts, then that would be more appropriately called work done by the gas, which would get a minus sign if we're talking about work. Sorry, if the gas contracts, that's work on the gas, which has the opposite sign as the work done by the gas. So we'll see examples of that to try to make that more clear when we would use the minus sign. So if we had suppose we want to go from 2 liters to 5 liters, and we're at 3 atmospheres, and we want the gas to do a lot of work. Well, there's a lot of ways I can go from this point to that point. We could just move straight across, or we could first ramp up the pressure, allow the gas to expand at very high pressure, and then allow it to, maybe I'm going to use different colors for these lines so that it doesn't look like I'm making a square. Or maybe we do something like this. We let the pressure expand. We let the gas expand while the pressure drops, and then we pump the pressure back up. So these are 3 different processes. These are 3 different processes. Each one would require a different amount of heat to be added to get it to occur, and each one would give a different amount of work output. Let's just try to compute how much work would be done on each process. So we have a process A, a process B, and a process C. If I want to find the work done on process A, I find the area underneath this whole thing. In fact, we could just shade it. It's not closed, is it? There's my gap. Okay, so that area would be the work done for process A. It's going to be 5 atmospheres times 1.013 times 10 to the 5th pascals. So making my pressure into pascals, times the delta V, which would be just 0.003 meters cubed. So I'm kind of using the fact that last time we saw 3 liters to turn it into meters cubed, you would divide by 1,000. So I'm dividing by 1,000 here. And that's 1,519.5 joules. Right, any questions there? We already saw that the work on path B, that was what we did in this last example, was 911.7 joules. To find the work for path C, we have to find the area underneath path C. So that hold on a second. Let me get that again. So I don't know why it's not filling in. There we go. So we do the work under that diagonal line, but the vertical red line, there's no area underneath that vertical line. So how do we find that area? Well, what we would do is we would break it into a triangle plus a rectangle. So that's going to be the area of the triangle plus the area of the rectangle. For a triangle, hopefully we remember from math class, the formula is 1/2 base times height. So that's the base of my triangle and the height of my triangle. And then for the area of a rectangle, it's just the base of the rectangle times the height of the rectangle. So that's going to be 1/2. The base is the 3 liters or 0.003, sorry, 0.003 meters cubed. And the height of my triangle is 2 atmospheres. It goes from 1 atmosphere up to 3. So that's 2 times 1.013 times 10 to the 5th. Then plus the base of the rectangle is also 0.003. And the height of the rectangle is just 1 atmosphere, which is 1.013 times 10 to the 5th pascals. So what do we get here? We get 607.8 joules. Okay, so 3 different paths to go from one point to another point. All 3 of those took a gas at 3 atmospheres of pressure and 2 liters and changed it to 3 atmospheres of pressure and 5 liters. But the path that we follow in this pressure V volume PV diagram is key to determining how much work is done. And that correspondingly is going to then mean different amounts of heat. Different amounts of heat are done, are used to make each of these processes occur. The change in temperature is the same for all 3 processes because we know PV equals nRT. If I have one pressure and volume, that's this point, there's a certain temperature at this point. And if I have a different pressure and volume, so maybe if I have a different pressure and volume at this purple point, that's going to lead to a different temperature. But it doesn't matter what process we follow, because we wind up at the same pressure and volume at the end, we wind up at the same temperature at the end. And since we start at the same pressure and volume at the beginning, we're starting from the same temperature. So all 3 of these processes have the same change in temperature because they just go from one point on the diagram to another. And each point on the diagram has a unique temperature. But the amount of heat has to change because the work changes. Let's look back at the first law of thermodynamics. So for all three processes, the delta U is the same. And since the work is changing, or I guess we'll look at the version with the work done by the gas. The delta U is the same for all three processes. So as the work goes up, the heat also has to go up in order to satisfy this equation. Okay, so we've talked about how to compute work. We'll get more practice on that next time. I want to talk about the change in internal energy. So the internal energy is just equal to the number of particles times the average kinetic energy of those particles. That's the total energy U. Now, we learned that the average kinetic energy is 3/2 times K Boltzmann times T. So that's, we could say it's 3/2 times N K Boltzmann times T. But that's related to the physics version of the ideal gas law. If we wanted to relate it to the chemistry version, we would use, instead of big N and K Boltzmann, we could write it as little n times R times T. So that means our formula for delta U is 3/2 times N times R times delta T. Now, I'm going to comment next time on this 3/2. I've been talking about it a few times already. There's this weird wording when we derive this result that there's 1/2 K Boltzmann T per degree of freedom, and there's 3 degrees of freedom. So that's where the 3 comes from. What we're going to see next time is that depending on the type of gas, whether it's monatomic or diatomic, this constant might still change. Okay, it may not always be a 3/2. So I don't want to get into that today because it's kind of a long story. But the main point for today is that if the temperature does not change, the internal energy of the gas does not change. Okay, and if it does change, we have an easy prediction on how it changes. As long as we know the number of moles and the change in temperature, then we can find how much the internal energy of the gas changes. So if we have a way to find delta U, and we have a way to find, so if we can find delta U, and we can find the work, then that means we can find the Q sort of by, you know, combining those other things. So in general, then the formula for Q is going to be delta U plus the work done by the gas. In our 3 different processes, the work done by the gas was different in all 3, but the delta U stayed the same, and so that means also the Q is different. So next class, we're going to be learning about different processes, different ways to move in this PV diagram, and how to compute the work and heat and delta U in those 3 different settings. The final goal is to learn how much work output we can get for an engine for a given heat input. We would like to learn how to maximize that number, that ratio. How much work can we get as output for a certain heat input? Like maybe we have a heat input into our machine of 1,000 joules, and we want to know how to get the most work out of it. Maybe we can only get 300 joules out. We put in 1,000 joules of heat, and only 300 joules of work comes out. So that would be better than a machine that takes 1,000 joules of input heat and only does 200 joules of work. So that's kind of our main goal. as we go forward. I think this is a good place to stop. Are there any questions about how to compute the work with the PV diagram in particular? That's the one thing I think we should have a handle on from today. But next time we'll be talking more about how to find delta U and how to find Q.